Hi class. In this lecture we look at the statistical data analysis tool that is available in Excel. Okay. To use this tool, you have to first go to the data tab and then go to the data analysis. And if you click on that, you'll see all the data analysis tools for statistical data analysis that are present within this tool set. Okay, there's roughly close to 19 options that you have here. We'll primarily look at just two options. We'll go through the um, regression tool and also the descriptive statistics tool. Okay, but one thing I want to make sure is that everybody has this enabled on their data tab. Okay, sometimes you may not have this feature present. So let's look at an Excel file here. Go here, and here you see that feature is not present. Okay, it was supposed to be present below the solver here in the data tab. It's not there. So what you do is go to file. Okay, click options, go to add-ins, and see if the analysis tool pack is in the inactive section. Okay, so you have to make it active. Select that and click go here, and then go click there, and once we hit OK, it should show up here. Okay, all right, so now we have that there. So once everybody has this, go ahead and click that. So when you click that, you'll see all those 19 options that you have here. Okay, that's how you find this tool if it's not already in there, and then you can use it. So going back to the PowerPoint, let's do a descriptive statistics example. Okay, so we will use a data set that I had given you before. It is basically measurement of factory flow rates of different units. So it's a factory test. So the flow rates are varying between different units. So we can find out a lot of these statistics, for example, average, which is the mean, um, using these functions. You can see what function I used: median, mode, standard deviation. So if you're a statistical person looking at the statistics of your data, you might be interested in all of these. What's the maximum value here? What's the minimum value here? How many data points did I measure? What's the overall sum? Um, some variance, standard deviation, things like that, standard error. So all of these you'll have to type in different functions. Okay. Instead, you could get all of that in one click using the descriptive statistics tool. So if you click that, you have to select the input range, and if your header is also part of the range, then you say the label is in the first row. Then you provide an output range, and then you tell them what exactly you're looking for: a summary statistics and the confidence level for mean. You don't really need this. At the very minimum, you have to click the summary statistics. Okay, you provide the output range, you'll get something like this in one click. Okay, one click of OK, you'll get all these values. Let's see how to do that. Okay, so I've already gotten these values. Like I mentioned, these are calculated using functions, and all of these values match. Let's recreate this section using the data analysis tool. Go here to data analysis, go to descriptive statistics, click OK. Input range, it's all the flow rates and the header. I could just use Control Shift down arrow, then output range. Output range, I want to select the top of this section so it plots in the same place. Then I want to select summary statistics. I don't really need the confidence level. Labels in first row, click OK. So now you've got all these values here. Sum, count, all of those values match. So that's how you get a quick statistical analysis of any given data using this tool. That's that's pretty easy. Now let's go and look at the second tool, which is regression tool. Okay. So for this tool, I had to build up a case as an example of using this tool. So what this tool does is if you give it a lot of x data, like x1, x2, x3, so different x's, y is a function of several x's, then it can fit a linear coefficient with all those x's using a regression um, method. Okay, so a good example for that is the polynomial developed by the AHRI standard 540. Okay, this is the standard in air conditioning, heating, and refrigeration institute that they developed, and it's to help the compressor manufacturers to um, provide the compressor performance. Um, so you cannot provide the performance for the whole range of operating conditions. So the compressors operate at several combinations of temperatures of the cooling side and the heating side. Okay, or I should say temperatures on the evaporator side and the condenser side. So they will operate at several different temperatures. Plus, there are other parameters too. Um, but let's just focus on these two temperatures for now. So they cannot test thousands of temperatures and provide the consumer the data. So instead, what we have seen is if you test certain level of points, let's say 15 or 20 or 10 points, 10 combinations of evap temperatures and condenser temperatures, and then you fit a curve using this polynomial, okay, using this polynomial with two variables here, temperature of evaporator and temperature of condenser, okay. So it's a third degree polynomial in the sense that the highest power here is 3, and you have cross terms here, so that sometimes you have TE times TEC square. So if you have an equation like this, and if you have a data set of temperatures, um, and then you also have the cooling capacity, power input, or the refrigerant blast flow rate, which are the performance parameters. Okay, when you're trying to look at the performance of a compressor, you're trying to figure out how much can it cool when the evap temperature and condenser temperature is so and so. How much power will it consume from the electrical line when the evap temperature and compressor is so and so? And what is the refrigerant mass flow rate? This is typically used by simulations, people who run simulations. So if you provide this curve to them, they can use this as a model of the compressor to run virtual uh, systems um, using dynamic simulations. Okay, um, so developing this polynomial is very beneficial, and it's already proven that this particular usage of variables using t squared e times tc gives good curve fit for the data. The most important thing to note here is what are the test points that you're using. So the test points should be well within the operating should represent the operating conditions very well. So operating condition, imagine it's a 3D map between temperature at the evaporator and temperature of condenser. It's a 3D region. All zones of that region should be represented to get a good fit, um, to get a good polynomial curve, which can be used for predicting performance at other conditions. Okay. So this polynomial equation allows manufacturers and engineers to predict compressors' performance under different operating conditions without the need for direct measurements. Okay, and it can be used for simulations and numerical models of compressor for figuring out which compressor to use for your application. Now let's look at a closer look here on the equation. This Y could be any of these. Cooling capacity, which is basically I don't know whether you're familiar with BTUs per hour, so that's same as watts. So it's the amount it can cool, amount of energy it can remove per second. So it's in unit of power. So it's watts or BTUs per hour. Power input is how much power it's drawing from the electrical line. So that's also in watts. Refrigerant mass flow rates, it could be in kilograms per hour, pounds mass per hour, or grams per minute, any of those units. Okay. So Y could be any of these things. So when the manufacturer is performing his test, he's basically changing the evaporator and condenser temperature and measuring these three things. And he will do that for 10 or 15 or 20 different points, and then find all these coefficients based on all those tests. So if you look here, there are 10 coefficients. So if you have 10 coefficients and 10 different combinations of T and Tc, you have 10 equations, 10 unknowns. So at a minimum, you need 10 equations to solve 10 unknowns. Okay. So the manufacturer needs to test at least 10 different combinations of evaporator and condenser temperatures. Some people test exactly 10, some people may test 15, some people may test 25. So it's varies from manufacturer to manufacturer. Another thing to note here is if you replaced these evap temperature and condenser temperature with the corresponding pressures, then also this equation works really well. Okay, so you can get a good curve using the pressure values too. Of course, the C1, C2, C3 values will be different. And also here, you have to understand that if the Y is cooling capacity, it will have one set of C1 to C10 values. And if you change it to um, power input, it will have a different set, C1, C2, which will, when it's put in here and the corresponding T and TC values are put in, you'll get the power value. So it has to have a different set of C1 to C10 coefficients. Okay. So the goal of this exercise is I will give you, or we have this data from the manufacturer. So he have more than 10 points. He has tested 23, he or she. They've tested 23 data points, um, and they have different combination of evap and condenser temperatures. And they have measured cooling capacity, refrigerant flow rate, and input power. Okay. Now, our goal is using this data, how do we find C1, C2, C3 to C10? Okay. If if there was only y equal to C1 plus C2 times dE, just a simple linear equation, it was easy to find. So you can just plot y and t in an Excel chart and use trend line to find these two. But now it's not just C2t, there's C3tc, C4te square. So it's not just one x, there's x1, x2, x3, x4. There are several x's up to x9. Okay, there are 9 different x's. How do you fit a curve on that? Okay, so that's a little bit tricky. The first thing to do is write down all the x's. Okay, so you have the evap temperature and condenser temperature. Write down all the different x's you have, the 9 different ones that we just talked about. T, Tc, T square, T times Tc, Tc square, T cubed, T squared times Tc, all of these. And then T is basically the evap temperature, Tc is condenser temperature. Use the equations to calculate these, okay, and just populate them downwards. So this will be just T evap temperature square. This is just multiplying this and this. So it's easy to create this um, table, okay. So now you have all the x's that are needed for the regression, okay. Now what are the y's? The y's for each regression could be either cooling capacity, input power, or refrigerant flow rate. So you'll pick one y here and all of these x's, and then it'll give you the C1 to C10 for that particular y. If you change the y, you'll get C1 to C10 of that particular y. Okay, and in this case, we picked cooling capacity as our y. So um, we open the regression tool, hit enter, and we get to this page on the regression tool. Here, the y, I've selected all the column here, which is u, and the x range is basically from k to s all the way down to 24. Okay, And I've included the labels because we're including the labels here. Okay, you're starting from row 1. And then you select an output range in your file, and you could choose to include residuals, but that's a good way to look at what is the error between predicted and the original data, and then hit OK. You'll get a full summary like this. One thing to notice to make sure your R square value is high. If you remember from our curve fit from Excel charts, high R square value means it's a very good fit. So this is a very high R square. So it's a very good fit of the data. Okay. And all the intercepts and the other coefficients will be reported here. So these are C1 to C10. Okay. So if these are the x's, these are the coefficients that needs to be multiplied, and this is the intercept that needs to be added. So it's basically that simple. Okay, as long as the R squared value is uh, is given to be really high. Now let's demonstrate this with actual data. Okay, so I have this chart. So these are my test points. So I've created these x values using these equations. Okay, and then I have this y, cooling capacity, input power. I think um, the mass flow rate is somewhere in there, hidden behind. Okay, but let's just try to find a summary, recreate this section of cooling capacity coefficients. Okay, so how do we do this? Go to data, data analysis, regression, okay, input y range. So I'm looking for cooling capacity in this cell. So I select the cooling capacity as my y, and the input x is all of these values, the 9 columns. Then include labels because I've selected the labels. Output range, I'll pick the same location, and I'll also include residuals. Okay, and click OK. It's trying to overwrite the data that's already there, so I click OK. So it's already overwrote everything that was on there. Okay, you can do the same thing for um, input power and refrigerant flow. Okay, each of them, basically these are the coefficients C1 to C10. So these values, okay, they're the coefficients. Now what else can we do with this? So you can copy these coefficients here of each individual thing. So for cooling capacity, I just copied all of them here. Okay, C1 to C10. I copied the ones for power here, copy the ones for mass flow rate here. And then you can verify these numbers using the equation. So I used these C1s to C10, multiply them with the x's here, okay, and we'll get a value here. So there is a small error. 110 is what the data point was. It's 111.15. So there's a small error, but that's within um, the R square equal to 0.99. But anyways, so you can calculate now what is um, what is the value here using this equation. So now you have an equation for a given temperature of the evaporator and the condenser to calculate the cooling capacity. Okay, within that operating conditions here, within this range of conditions, it should be accurate. Outside that range where the data is collected, it will start becoming inaccurate. So that's why this original data set that the manufacturer tests is very important. You can create similar equations for input power which using these coefficients here, and also for input refrigerant flow rate. Sorry, yeah, the calculated refrigerant flow rate. Um, Now, if I wanted to find a temperature that's not in this list, so a combination that's not in this list, in this case, let's say 10, 45. So 10 is reasonably in the middle of this. Maybe I should pick 5. So let's pick 5 degrees because it seems like it goes from minus 23 to 12. So let's pick a value in the middle here. And it's here it goes from 26 to almost 62. So I think I'll pick maybe 45 is good, or maybe I'll pick 50. Okay. So I can pick this value, and then I can get the additional x's by just um, dragging them down. So it's automatically calculating for 5 and 50. Then all I need to do is calculate using this equation, drag it down further. So for new temperature combination where there is no test data, I'm able to predict what the compressor will do. So we know the cooling capacity for 550 is 292.91 and 92.91 and 4.2 for refrigerant flow rate. Okay, so this is one of the benefits of having an equation um, where you can predict the performance. Okay, in one of the assignments, you'll have to do a uh, coefficient. You'll have to find the coefficients, and then you'll have to find the value for a new data set or new data combination, which is not there in your original data set. And you'll report that number in your assignment back. Okay, so that's all there is to it regarding the regression. We can discuss more in class. Thank you.